Function arithmetic. Arithmetic just means add, subtract, multiply, divide. It is the basics, the stuff that you learn first. And function arithmetic is when you do that with functions. So here we have f of x and g of x, and we are going to do some arithmetic with them. The first thing that we're going to do is add them together, and the way that we can write that is f plus g of x. Now you can write it like this. You can also write it as f of x plus g of x. These mean the same thing, but I will use this more often just because it's the more common notation for adding two functions together. When we subtract, this will be a minus sign, right? Multiply, it will be a little dot, or just f and g together. And then division, though, it'll be a fraction. So when we add these two together, we're basically combining like terms, right? We can add in either order. It doesn't matter because addition's commutative, so we can put this first, then add this, or write g of x first. It doesn't really matter, but we'll just go in order. So we'll add f of x, which is 2x plus 1, and then we'll add g of x. With addition, no parentheses are necessary, although it's not wrong if you put them around each individual function. Now we're just combining like terms. So we have 2x and 1x, and then we have a plus 1 and a minus 5. So this is our new function. We have the function f plus g of x, and it equals 3x minus 4. So we have now created a new entire function. We've added two functions together and created a new one. What can we do with a new function? Well, a lot of times you might be asked to find the domain. So let's do that. Let's find the domain of our new function. And the reason that we want to find the domain is because the domain kind of tells us the rules. It tells us what can we plug in into our function to get out a viable solution. When you combine two functions together through addition, subtraction, multiplication, or division, you create a new one, and so the domain might change from one of the original two functions. Now, if we look at our original two functions, they are both just linear, right? If we graph this, either one would just be a line, and they're just regular old polynomials. There's no rational functions, right? There's no x in a denominator, there's no square root, there's no x under a square root. And so therefore, because they're just regular old polynomials, in this case linear, our domain is just going to be, for each one of these, is all real numbers. Now, when we add them together, did we create anything mind-blowing? Did we create anything new or different? Not really. This is still just a regular old polynomial. It's a linear polynomial again, and this would just be a line again. There's no x in a denominator or in a square root. Therefore, our domain of this new function is all real numbers, negative infinity to positive infinity. Let's do one other thing with this new function. Let's evaluate it at a point, at a value. So let's find f plus g of negative 2. All that means is this is our new function, f plus g, that's its name, and all this means is let's plug negative 2 into this new function. So we're going to have 3 times negative 2 minus 4, which will give us negative 6 minus 4, or negative 10. So these are just a couple things we can do with this new function that we've created through arithmetic. The next thing that we'll do is subtract the two functions. Now, subtraction is more specific than adding because the order does matter that we subtract. In this case, we're going to start with f and then subtract g. We could go the other way, and we'll do that next, but we're going to start with f of x, which is 2x plus 1, and then we're going to be subtracting g of x, x minus 5. Now, we definitely need the parentheses around this because when you subtract, you're technically distributing a minus sign through. You're distributing a negative 1 through. So we do need parentheses with subtraction. So we'll have 2x plus 1, that doesn't change. Then we distribute our negative, so we'll have minus x, and then we'll have plus 5, because when we distribute that, it's like minus a negative 5. Now, I know a lot of you are looking at this like, yeah, duh, I definitely have to distribute a negative. But I will say that this is one of the most commonly missed skills or little parts of of subtracting two functions is distributing that minus sign. I can't tell you how many times students think that this is obvious, but they'll keep a minus sign here. So just be careful when you're subtracting more than one term. Make sure it's in parentheses and you distribute. Okay, now we can combine like terms. So we have a 2x minus an x, and then we have a plus 1 and a plus 5. So our new function, f minus g, is again just a linear polynomial, and it's nothing crazy. So its domain, once again, is still all real numbers, and then we can evaluate it at really anything. So this time let's evaluate at a variable. Let's evaluate at a. So that means I'm going to plug in an a here for x, and so when we evaluate at a, we'll have a plus 6. Next, we'll multiply f times g of x. So we're going to take 2x plus 1 and multiply it by x minus 5. And we have two linear polynomials here. Specifically, they're binomials, right? They each have two terms. And when you're multiplying two pairs of a pair of binomials, you can think of FOIL, or you can just think of multiplying using the distributive property. Either one is fine, however you want to think about it. So when we multiply this, we'll do 2x times x and then 2x times negative 5 first. So we'll have 2x times x, which is 2x squared, and then 2x times minus 5 minus 10x. Then we'll take the 1 and distribute it to both terms again, and we'll get minus 1x and then minus 5. Then we'll combine like terms. We have a quadratic term now, and we have minus 11x and then minus 5. So this is kind of an interesting one. Unlike, addition and subtraction didn't really do anything that crazy, but multiplication kind of changed the game a little bit here. We started with two linear binomials, and when we multiplied them, we created a new function that is a quadratic trinomial. So we have gone from linear, right, where it's just x to the first, to quadratic, x squared. And so this has the potential to change a couple different things. It's going to change what the graph looks like. This would now be a parabola, whereas these two individually would just be lines. Let's take a look at its domain. We still do not have x in a denominator, nor do we have x under a square root. We can plug in anything we want into these x's, and we're not restricted. And then if you were asked to evaluate this, we totally could. Let's plug in a variable expression. Let's plug in x plus 1. When we plug in x plus 1 to this, we have to plug it into both spots where there's an x. And then when you multiply out x plus 1 squared, it's x plus 1 times x plus 1. So that is x squared plus 1x plus 1x, which is plus 2x, plus 1. We'll distribute the minus 11 through. And then we have the minus 5. We'll distribute the 2 through. And once we clean up a little bit more and combine like terms, this is our final polynomial, again a quadratic trinomial. So I'm just doing a couple things to review a few things that we've done earlier in this chapter as well. So far with f of x and g of x, we've added, subtracted, and multiplied, found the domain of each new function that we've created, as well as evaluated at a point, variable, or a variable expression. The last thing that we can do is divide, and division really just means make something a fraction and then simplify if you can. So this is f over g, and so we'll put f of x in the numerator and g of x in the denominator. So subtraction and division are actually the two where the order definitely does matter, right? Subtraction, it matters which one you put first. Division, it matters which one goes in the numerator and denominator. Can we simplify this at all? We have to look and see if we can factor anything. So we cannot factor out a GCF in the numerator at all. nor can we in the denominator. So this is actually our final answer. Now this is a good one for when the domain changes. Look at what we have now. We have a rational function. Rational meaning x is in the denominator. We are going to have some restrictions on our domain now. We can't plug in anything that we want. So let's take a look at our denominator. We need to see what makes the denominator 0. It does not matter if the numerator is 0. You don't care about the numerator, only the denominator. Well, this one's really easy to look at. It doesn't take any work. The value that makes the denominator 0 would be 5. So we know our little thought bubble is telling us x can't be 5. That means that our domain is all numbers except 5. So we'll start at negative infinity, go up to 5 but not include it, jump over 5 to the other side of 5, and go all the way to positive infinity. So our domain has changed, and almost always it will change once you divide because you've literally created a fraction. Let's plug in a value here and evaluate it. Let's evaluate f over g at 3. When we evaluate at 3, we'll have 2 times 3, 6, plus 1, so 7 in our numerator. And in our denominator, we'll have 3 minus 5, or negative 2. In mathematics, the reason that I picked a number that would give us a negative in the denominator is to show you that you do not want to write your final answer like this. Obviously, this is a negative 7/2, but we don't want to write the negative in the denominator. Instead, we write the negative either in the numerator, or you can write it out front of the fraction like that. So these are two good ways to write your final answer as a negative. You don't want to write it looking like this. In our next example, we have a new f of x and g of x, and we will do the four arithmetics, I guess, and then find the domain of each new function. So let's first add them together. Remember, adding together is really just combining like terms, so I'm not even going to write it all out. We're going to add together the x squareds first, so we'll have 2x squareds. Then we can combine the linear terms, negative 2x, and there's no linear term here. Then our constants, negative 3 and negative 9. Cool. Now, if you'd like, we can factor out the 2. This is just a practice in factoring. The greatest common factor here is a 2, and so we can take that out front. Basically, we're just reverse multiplying or reverse distributing. So out of our first term, we'll have an x squared left. Our second term will have an x, and our last term a minus 6. This can factor even further, and we can do that next if we'd like. So this is a totally appropriate way to write your final answer. But then we can keep factoring here just as an exercise in factoring. Two numbers that multiply to negative 6 that add to negative 1 are going to be a minus 3 and a positive 2. If you were to FOIL this out or multiply it out, we'd have x squared plus 2x minus 3x, which combines to negative 1x, and then minus 6. So this is just a factored form, which we will do some factoring, so this is just a good exercise. So this is called standard form, and then we factored it and got factored form. Not everything will be factorable. This was our first one that really was, so that's one way to write it. Let's take a look at the domain. If we take a look at the standard form, that's the easiest way. We can see that we just have a quadratic trinomial, just a regular old polynomial. So our domain is all reals. Next we'll subtract, and in this time I'm going to start with g. So we'll start with g of x, and then we're subtracting f of x. Again, you need parentheses around what you're subtracting because you're going to distribute the minus sign. So we're going to distribute that minus sign. So we'll have x squared minus 9. Then we'll have minus x squared plus 2x plus 3. Then we can combine like terms. We have two quadratic terms. We have a positive x squared and a negative x squared. So those actually cancel out. Then we have a 2x, and then our constants are a -9 and a +3, so that'll combine to a -6. So this is a totally acceptable way to write your answer. And then if we want to factor it, we can take out the GCF, which is 2, and we're left with x minus 3. If you ever want to check if you factored correctly, multiply it out, and if you get back to your original, then you did it right. All right, our domain here, once again, is all real numbers because we just have a regular old polynomial, in this case a linear binomial, 2 terms, and no x's under a square root or in a denominator. Next, we're going to multiply, and I already wrote them out. So with multiplication, we are going to be distributing. So the first thing we're distributing is the x squared. And so the x squared will get distributed to this x squared and then the -9 first. So first we'll have, careful not to write 2x squared here, that would be adding. X to the second times x to the second is x to the fourth. When you're multiplying with the same base, you add your exponents. Then we're doing x squared times -9. Okay, next we are going to be distributing this -2x to both. So we'll have -2x times x to the second. So this is x to the first times an x to the second is an x cubed, and then we have that -2. So -2x cubed. Then -2x times -9 is positive 18x. And then last, we're going to distribute this -3. So we'll have -3x squared and then plus 27. So be careful. Common areas to make mistakes here are not getting the correct exponent and then a negative times a negative and not writing a positive. So those are just common mistakes that you can make. All right, when we're combining our like terms here, we have a quartic term, x to the fourth. Then we have our, whoops, those aren't the same. We only have one cubic term. Then we have 2 quadratic terms. Then we have only 1 linear term. And then we have only 1 constant. So this is a very long polynomial. It is a 5-termed quartic polynomial. Its domain, once again, is all reals. Next, we are going to do some division. All right, our last thing, we're going to find f divided by g of x. So we'll put f of x in our numerator, and we'll put g of x in our denominator. Now, there's no greatest common factor in the numerator to factor out, nor is there one in the denominator. However, the numerator can be factored. And if we look and see, the numerator is a quadratic trinomial with a lead coefficient of 1, right? It's 1x squared. So in order to factor it, we want to see if there's 2 numbers that multiply to -3 that add up to -2. Those numbers are a -3 and a +1. Again, if you were to multiply this out, you would get back to this original polynomial. And that is a way to check if you factored correctly. So factoring is entirely self-check. In the denominator, we have a difference of squares. This is one that students forget a lot too, but it's really easy to factor. This is a perfect square. Its square root is x. 9 is a perfect square. The square root's 3. And it's a difference, minus. So it factors into each one of the square roots, 1 plus and 1 minus. Again, if you were to multiply this out, you would get back to the original x squared minus 9. So let's find the domain before we cancel anything. I know we can clearly see that there's an x minus 3 on the top and bottom, and we will cancel those. But before we do that, let's find the domain. We can see that there are some values, specifically 2 values, that make our denominator 0. Here, the value that makes this 0 is -3. Here, the value that makes this 0 is 3. You could have seen that from the beginning too. If you plugged in -3 or +3, here you'd get 9 minus 9, which is 0. So we can't be 3 or -3. And so therefore we have to exclude those values from our domain. Again, we don't care about the -1 up here. Yes, that makes the numerator 0, but we don't have to worry about the numerator with domain. It's only the denominator because we can't divide by 0 in math. So we have to skip over -3 and +3. So we have to travel all the way from -infinity to +infinity, but we have to skip over those two values. So this is our domain. All right, now how can we write this as a very final answer? This x minus 3 and x minus 3 can cancel because they are factors that are the exact same in the top and the bottom. And so our final answer can be written as x plus 1 over x plus 3. That is our function f over g of x. Now it doesn't look like a 3 would be an issue here, but it really is. So you do have to find the domain before you do any canceling. And then we'll get more into this later in the year, but these two values of -3 and 3 that are issues, they are asymptotes in our graph, or they're holes in our graph. All right, so the main gist of today's lesson is that we can add, subtract, multiply, and divide two functions. That's called arithmetic with functions. And then when we do that, we create a brand new function. It has a new name that looks like one of these. When we create a new function, we potentially have a new domain or values that we can plug in. So we do have to be aware that once we find a new function, we do have to find its new domain as well.